Hello everyone, welcome to Mark 1 Design EMC channel. Today's session, we're going to demystify immunity tests. Now, what you just saw is a typical immunity issue. In this particular case, the screen started flickering. Now, when it comes to immunity, obviously the victim is our product or our system, but where does the noise source come from? There are many types of noise sources in our daily life. For example, simply a walkie-talkie creates what we call narrowband noise source. And if your system or product is not designed against this type of noise, your product may suffer issues as what we saw previously. Or in this case, an electric motor typically will create noise in the lower frequency range, normally between hundreds of kilohertz all the way to megahertz, such as this. In a higher frequency range, typically 80 or 100 megahertz above, we'll see coupling mostly through radiation. Now, the products we design will pick up noise, and there are generally two ways of picking up noise. One is via the PCB itself, and then the other one is the cable. In the higher frequency range, typically 80 or 100 megahertz above, our product will start picking up noise by both the cables and the PCB itself. This is because at higher frequency range, the frequency is high, hence the wavelength is short, therefore tracks and traces on the PCB start becoming efficient antennas to pick up noise. In the same time, cables also pick up noise. In this case, we're going to simulate an ESD event by using this spark gap generator. We have the antenna attached to it, which means an ESD event will happen and then radiates out. And as you can see here, the PCB will pick up the noise very easily. And as we know, an ESD event is a very high frequency event. So typically a PCB trace and track can pick up this noise. As we can see, it is necessary to test a product from the immunity point of view. That is why the standards defined the so-called radiated immunity test. So during the radiated immunity test, we have an antenna which is connected to a high power amplifier, feeds the amplifier using signal generator. Then we put all this radiated power into the device on the test. This distance between the antenna and the product is often 3 meters or 1 meter, depends on the test standards. Now, it is important to achieve what we call unified field area or UFA, because if you want to test the product thoroughly, you would ensure that across the wide frequency range, the electric field or the electromagnetic fields that you impose on the products should be consistent at the same level. This becomes very tricky when the frequency is below 80 megahertz. This is because, as we said, at high frequency, the product can pick up noise either by PCB or cable. But in the lower frequency range, this coupling becomes predominantly via cable. As cables have different lengths and cables can behave either like a quarter wavelength antenna or a half wavelength antenna. Now, to achieve this unified field area in the lower frequency becomes very challenging. Now, some clever people in the EMC field start to think of a better way of testing lower frequency immunity. And then they come up with this idea of CDN. CDN stands for coupled decoupling network, provides a constant impedance. And when I say constant impedance, I mean the constant common mode impedance. And standard defines that impedance level at 150 ohms. What does that mean? It means between 150 kilohertz all the way to 80 megahertz, the device CDN, such as this one, provides a constant common mode impedance of 150 ohm to the product on the test. Now you may ask, why do we need 150 ohm? Where does that number come from? Well, this is a good question because as we said this before, different cable lengths will have different resonance frequency, and it is simply impossible to test an infinite number of cable lengths, right, across the frequency range. So we basically take the mean value of a common mode impedance of different cable lengths, and the mean value, it is 150 ohms, because typically a common mode impedance of a cable, again, depends on its connection and things like that, ranges from 30 ohms all the way up to hundreds of ohms. So 150 ohm is the mean value of the common mode impedance value, representing a resonance cable structure. Okay, so knowing that is very important, because the whole idea of the conducted immunity test is really to test the coupling capability of a cable to the device on the test. Therefore, the CDN, as the name suggests, coupling and decoupling. So it couples the noise into the device on the test and decouple the noise from whatever supporting equipment we have for the device. Now, let's have a look at the details. We're going to use this document called Conducting Immunity Basics to explain the basics, the calibration and test of a typical pre-compliance conducting immunity test. TechBox produced this document, and I've also put the link in the show notes so you can check. If you go through this document, it explains both the CDN and the bulk current injection methods popular for conducting immunity tests. We are going to talk about the BCI test in a separate video. As explained, we need 150 ohm common mode impedance. It is worth mentioning that most of the CDNs are characterized all the way up to 230 MHz rather than 80 MHz. This is because under certain scenario where the product is quite small compared to the electric length of the cable, you can test the product in theory all the way up to 230 MHz using a CDN method, but most of the cases we test up to 80 MHz for the reason we explained. Okay. Now I wanted to bring your attention to this simplified system diagram of a CDN. As explained, the coupling part of the CDN is through the capacitors, C1 in this case. And as you can see, this is a M3 CDN because we have 3 lines in and 3 lines out. To achieve 150 ohm impedance, what the manufacturers do is they put, for example, again in M3, 300 ohms in parallel. This gives you 100 ohms resistance or impedance in total, plus normally you have 50 ohm source impedance coming from the generator side. That gives you 150 ohm common mode impedance. So as you can imagine, a noise or signal you injected to the input, and then through these capacitors, noise will go to the product, which is normally connected to the EUT port. The decoupling side of CDN consists of inductor, because at higher frequency, inductance become high impedance, so that during the test, this part of the circuit will block the RF noise you inject. Therefore, the noise will not affect the AE port, which is often connected to the mains power supply or any other supporting equipment. Thus, the name of CDN, it's decoupling the noise from here and coupling the noise to the product on the test. Okay, now this shows you the basic test setup. The important thing here is the 10 centimeter insulation support, because that gives you some parasitic capacitance between DUT and the test ground plane, and that is often in EMC term we call it provides the return path of the common mode current you inject into the system. Other details relating to the test setup will be discussed later in this video. Okay. Now this table defines the test level in the test standards. Generally, you have 3 different levels, with level 3 being the highest, and we define that level, that severity, by monitoring the output voltage out of a CDN. In this case, as you can see, the open circuit voltage. Of course, you can test even higher level by your own standards, so that you can stress the product even further by simply putting more power to the amplifier. Therefore, you test a higher voltage level. It is worth mentioning that, as you can see here we have two different waveforms. One is what we call unmodulated RF signal or continuous wave, and the other one is the amplitude modulated wave. The standard 61000-4.6 always defines test as product using AM modulation, right? But if you look at the two waveforms, you can't help but notice that in order to achieve the same RMS open circuit voltage, you surely need more power to drive the amplifier with AM enabled, right? With AM enabled. And that power difference, as is explained here, is 5.1 dB. So you need 5.1 dB higher amplifier power, RF power, with AM enabled compared with continuous wave. Why do we need to know the difference? Because the calibration process, normally you calibrate the conducting unit test with continuous wave, right? Because that's simply that is more accurate. Now, the general procedure is you calibrate the conducting immunity test setup using continuous wave, and then when you test the product, you enable the AM and then put 5.1 dB higher power in the output of your amplifier. Now this is achievable if you just note down the value during the calibration, and then when you test it, always remember add 5.1 dB more to the amplifier. But it could make life much easier if everything is automated in a software controlled manner, right? So that is why if you go down here, we'll show you the calibration using a software method. So this shows you how do we calibrate the conducting immunity test using EMC View Pro software. Now, as we mentioned, during the calibration, you simply use unmodulated wave or continuous wave, and the software basically records the required signal source level to the amplifier to achieve, let's say in this case, level 3. This calibration file will be then saved in the software. Now when you test the system, you simply enable that AM switch, and the software will automatically add that 5.1 dB more power to the amplifier, making sure that the stress level achieve the desired voltage level that you require. We'll explain this in the setup in details. Okay. Now, because the radio frequency noise is often coupled into the system via parasitics, right? Parasitic capacitance or parasitic inductance. Therefore, to perform a conducting immunity test, the setup is of critical importance, because small difference in the setup can often lead up to big difference in the test results. And this really could mean a simple pass and fail for your product. If you tested wrong and you injected higher level of noise into the system, you may fail the product and you will spend enormous amount of time redesigning your product while knowing that it could have potentially passed. Now this has a big impact on the product to market time, because obviously you don't want to over-engineer your product, therefore you spend lots of money on the product which really you don't need necessarily to spend money. Therefore, it is very important for us to understand the conducting immunity test and its setup. Knowing the importance of conducting immunity test setup, now the first thing we need to do is to calibrate the test setup. So this session we're going to look at how to calibrate a CDN test setup. We're going to use a CDN M2 type for demonstration purposes. As you can see, it is an M2 type CDN, meaning it is normally used for mains powered product, but without the earth connection. So we're going to get live and neutral, or it could be also high voltage or low voltage DC powered product, right? And so we got the CDN M2 here. We also need a calibration kit. So if we look at what's inside the calibration kit, we'll see there are two plates, and these plates, as you can see here, on the first line there were 3 holes and second line is 2 holes. This really if I show you the bottom of this, you will see the 3 holes is to mount it into this 1, 2, 3 points, and 2 holes you will see later. So we got 2 plates here and 2 adapter, and this adapter is called 50 to 150 ohm adapter. As we explained, 150 ohm as a common mode impedance is very important. Therefore, for calibration, we need these adapters. And what's inside here is we need this adapter plate. So as you can see, this is a adapter plate designed for calibrating M2 type CDN. Therefore, there are only live neutral or positive and negative inputs. As for M3, you will find often you will have 3 pins here. So this is designed for M2 and used for M2. And you need 2 of these. What else have we got here? We got 6 dB attenuator, 50 ohm terminator, and another 30 dB attenuator here, plus some screws, nuts and bolts here. And okay, let's connect the calibration kit. Let's have a look at the calibration setup. As you can see, the plates we now fastened to the CDN by the screws, and you can see 2 screws here, and behind the plates there are 3 more, which you all need to fasten them. And on the back of the, well, on this side of the CDN, we do exactly the same. Okay, so making sure that a really good contact between the plates, the adapter, and the CDN. So everything now is connected properly. Here we have on the auxiliary equipment side or AE side, we have the adapter, and of course, as we mentioned, this is the 50 to 150 ohm adapter, and this is a 50 ohm terminator. So altogether, they represent 150 ohm common mode impedance. So which makes sense, as we said, we assume all the cable connection as 150 ohm common mode impedance. So this side represents the AE side of things, right? Now noise is going to be generated from this port and then coupled to the EUT side. So that's on this side of the CDN. And on the EUT side, we have very similar structure. We got the adapter plate, we got the 50 to 150 ohm adapter, and this is connected to the spectrum analyzer, which has a 50 ohm input impedance via a 30 dB attenuator. As you can see on this end, on this side of the CDN, during the calibration or during the test, lots of noise will be coupled to the EUT side, and therefore, if we want to use the spectrum analyzer to receive signal, we need something like a 30 dB attenuator before we can measure the signal. Otherwise, the RF input front will be blown up. So we definitely need this 30 dB attenuator here. 6 dB attenuator is needed according to the calibration procedure. So that's from the RF input port, we got this 6 dB attenuator, which is connected to the output of this amplifier. As you can see, for this calibration, we have the CDN 25 from TechBox. This has 25 watts output maximum power, and it has the frequency range between 100 and kilohertz all the way to 250 megahertz. So more than enough in terms of the frequency band, and also the power should enable us to test the highest level for CDN, which is level 3. Okay, and as we can see here, this is a closed loop system. So the spectrum analyzer, the tracking generator of the spectrum analyzer provides a signal source going to the amplifier. Amplifies our signal, gets into the CDN, coupled into the EUT, and then we measure basically the voltage from the input side of the spectrum analyzer. And the whole thing, you can automate the whole thing using a EMC View software, which we are controlling this using this laptop to control the whole closed loop system. So in order to test it using the closed loop, you need a EMC View software professional version, pro version, let's call it. And again, now it is connected to our spectrum analyzer. So all we need to do is go to mode and select immunity. And you can see this interface shows you the closed loop system exactly the same as what we had there. You can see here we have the CDN25 as the amplifier, the CDN, which is M2 in this case, and then we want to calibrate level 3, as we said, to start with. And all these numbers, bear in mind, they're just there for reference only. It's very easy to operate this calibration. Simply power the amplifier, power the spectrum analyzer, and then click calibrate. The whole thing should be automated. So let's try it. So now switching on the amplifier, and as we say, currently we select level 3, and everything we've already defined. The calibration will be performed between 150 kilohertz all the way to 80 megahertz. Okay, very simple. Click calibrate, and then we should be able to see the system start to performing. As you can see there, the spectrum analyzer start to scan step by step, and as here we can see the results. So altogether it's going to perform 17 segments. Now it's at 3 out of 17, so we just need to wait until it's performed. And so as we explained, the amplifier basically amplifies the signal, and then this end reads the signal. Then, you know, for level 3, according to the standards, we just adjust the signal input to the amplifier, therefore maintain a constant noise level across the whole frequency range. Okay, so now it is 8 out of 17. We just need to wait a few more points before it is ready. As you can see, so to achieve level 3, we need the tracking generator output minus 6 dBm at this frequency range. That's really it. So this will be then saved as a calibration file. Once it is saved as a calibration file, then we can start performing the conducting immunity test very easily. Okay, right. Calibration done, no errors, great. Once the calibration is done, we need to save the calibration file. So save calibration file is here. And so we basically click save calibration file. As you can see, I have some predefined calibration file already. So for this one, we can call it CDN level 3 continuous wave calibration file. Okay, so we'll save that. And then when we finish the calibration, all we need to do is basically disassemble the calibration setup, sets the CDN as per standard, and then we can load the calibration file and then control the conducting immunity test using level 3 for the test, which we'll demonstrate later. It is worth mentioning that this power amplifier also has the modulation mode. So currently, as you can see, previously we performed the calibration without the modulation enabled. As you can see, now we have disassembled the calibration setup and we set up the proper conducted immunity pre-compliance test setup. We have already demonstrated this setup in a separate video, so you can watch that video as well. For this video, as you can see, the most important thing is that the CDN needs to be bonded really well to the test ground plane, as we explained, because this coupling and decoupling is very important. So test ground plane needs to be bonded, electrically bonded well to the test ground plane. And here, as you can see, 6 dB attenuator, we're still keeping it. And this part of the setup is exactly the same. Spectrum analyzer provides a signal source, amplifier, amplified noise, and then get injected into the CDN. As you can see here, this port is the EUT port, which will be connected to the device on the test. The other port is the AE port, which in this case connected to the power.
Now, the most important thing, as I said, one is to bond the CDN properly to the test ground plane. The insulation support has to be 10 centimeters defined by the standard. The reason for the insulation support is because this provides a capacitive coupling between the device on the test and the test ground plane, and that is the return path for the common mode noise injected into the system. Think about it. Common mode noise get injected to the cable structure, arriving at the EUT, and then it is through that parasitic capacitance it comes back. The surface current will be flowing on the test ground plane back to the system. So that is important. That gives you a defined parasitic capacitance, let's call it, to finish the loop. And another thing, as we mentioned before, is the cable length. As according to the standard, this length has to be less than 30 centimeters, because if you're using longer cables, then of course you defeat the purpose of the CDN, which is to provide a constant common mode impedance. And saying that's it. Now we need to power the unit, power the spectrum analyzer, and power the amplifier to perform the test.
Of course, enable the modulation that will give you AM or PM modulation, and to do that in the software you also have the option of modulation AM, so you can select that.
Okay, so once the pre-compliance conducted immunity test is properly set up, we can move back to TechBox EMC View software, and as I said, the to perform test is extremely easy and straightforward. So the first thing is, of course, to load the calibration file. In this case, we just select the calibration file we saved a couple of minutes ago. Obviously, you have many other calibration files you can select, but in this case, we'll just select this one. And by default, the starting frequency is 150 kHz and stop frequency is 80 MHz as defined here. And here you can change the frequency step sweep by percentage. So in this case, it's gonna do the 1% sweep, or you can select the dwell time as seconds as well. So that means at each point it will dwell for 1 second. And yeah, of course, you can also define your own starting frequency for troubleshooting, for example, because in this case, if we perform tests, it's going to take a long time. And if you find the EUT is particularly susceptible to certain frequency band noise, then of course, then you can focus in that frequency band only. Okay, and of course, you can enable amplitude modulation as you wish, but in this case, we're going to just perform the continuous wave because the calibration file is saved as continuous wave. Okay, so without further ado, we can start run, and as you can see, is starting, and really the software is telling the signal source, in this case is the Rigo spectrum analyzer TG tracking generator output, to output -12 dBm in this frequency range, so that the output voltage can achieve level 3 in the CDN test. And that's as simple as it is. And of course, as we explained, it will take time to finish the whole sweep. As you can see here, it's 200 kilohertz now, and we're gonna wait for a long time until it's finished. Okay, so for that, we're gonna stop it. And because I knew this system, this device on the test, which is a small LED light product, is particularly susceptible to noise in sort of 40 to 50 megahertz range. Therefore, I'm going to select 40 megahertz, and I'm going to stop at 50 megahertz. Right? I'm going to select at stop at 50 megahertz. Did it wrong? Yeah, let's do it. 50 megahertz. Okay, so I'm gonna start doing that. Yeah, so now it starts from 40 to 50, and then you will see, as you will see from the next video, the lights will start flickering.